Welcome to Chapter 6 of the Reading the Robot Mind book. We're going to go over a simple RTRM example using a multi-layer perceptron, otherwise known as a dense or fully connected neural network layers. Today I'm going to answer a real question that someone asked me on Reddit just yesterday. So here's the exact comment I received. The person said, since it's attempting to reconstruct the input given the output of a specific layer, what exactly does checking that predicted input for different layers of a model tell you? Besides finding which layer approximates the input best, what information or utility can you get from layers that don't approximate well? Well, that's really a great question. I'm going to answer it right now using the exact example from the book. So here's our toy classification problem. It's a really purposely kept simple as a kind of an early example in the textbook. We have two rings. You can see those two rings, one red and one blue. The red outer ring, we'll call that class 1, and the blue inner ring is class 2. So a human could instantly see which points belong to which class. But it's not as though we can separate them with a straight line, so we do need to train a neural network to solve this problem. I've also placed a few probe points, those yellow stars. We're going to use those to test the model. So this is the exact multi-layer perceptron that we've trained. It's got 5 layers. There's 64 neurons in layer 1. There's 30, then 32, then 16, then 8. And then finally, there's a single output neuron that will say, is it class 1 or class 2? So let's watch what happens inside this neural network using 3 different reading the robot mind methods. We'll look at all 3 methods side by side on the exact same probe point. So first, the pseudo-inverse. That basically mathematically calculates backwards, just making linear best estimates of the input by multiplying by the weights and adding up their contribution to that input. So we're basically working backwards through the weights of the neural network, but we're only considering the linear aspects. We're not going ahead and doing the inverse hyperbolic tangent or anything like that. We'll also take a look at a brute force method, and that means we're just going to save a huge bunch of training examples to disk drive, and then we're going to present the neural network with some new data point, and we'll see what each layer outputs for that new data point. Then we'll go ahead and pick the training examples from that disk that made very similar or close outputs at that layer. All right, we'll see how that looks. And then finally, we're going to take a look at the autoencoder. The autoencoder basically trains a whole new neural network for each of those layers, trying to take the output of that layer and map it to the original input, or basically train a neural network that will try and recreate the original input. This is the most realistic of the recreations, but it is the most computationally expensive to calculate because you have to train a brand new neural network for every layer to go ahead and try and recreate the original input. So each of these methods reveals something different, and even a non-programmer can understand what's going on. Let's go ahead and take a look. So the pseudo-inverse method is only using linear math, just multiplying by the weights and adding them up, kind of just like the forward pass of the neural network, except now working backwards and also ignoring any non-linearities. So it really takes the output of a particular layer and tries to recreate a best approximation of the original input. So you can see that every layer gives you a sharp reconstruction, but it is distorted because of the nonlinearity of the real neural network. But also, as we go deeper, you can see that the reconstruction stops reconstructing sort of what we originally saw, which was rings of data, but instead just kind of creates these blobs. At first, a little bit bigger, a blue one and a red one after the third layer 2, the third layer there. But then those blobs become just dots. Really, this loss of information or loss of detail about the original input is not a failure. It's actually the model deliberately discarding everything except for the classification that it was trained to perform. So that's really we call that the pseudo inverse. It's the quickest way to go ahead and perform a reading the robot mind system. Just quickly see where the information is pretty much discarded in favor of classification signals. So now let's take a look at the brute force method. And I think this is really a great way to explain how reading the robot mind can be used to talk about how a neural network works to somebody who isn't a programmer. So these six panels, these five pictures here, go through each layer and watch what happens as we move deeper into the layer. So these early on from our probe point, that's that little star here, we see that the training examples that produce outputs at that layer that are similar to the outputs of the probe point are really the ones that are physically closest to that probe point. So early layers, the reconstruction looks almost like the original input. Still, as we go through layers, we see that mostly physically nearby examples produce outputs that are similar. But soon, by the time we get to this third picture or layer two, something is changing. The closest points are now starting to respect those class boundaries. By the time we get to layer three and the final layer, the decision is basically already made. The final layer, the model has thrown away pretty much all the original information about where the probe star was taking place in the X, sort of in that two-dimensional graph. But also, it's only kept the information about what class, basically which ring am I on. So the layers that reconstruct the input poorly are actually very valuable layers. They're the ones that show you exactly where the artificial intelligence solution made its decision. So here's the big insight. The classification decision was kind of locked in two layers before the final output. We saw that both with the pseudo inverse, the linear recreation of the input based on the outputs of a layer, as well as the brute force, where we just looked for examples whose output at that layer were very close to the output of our test probe point. A domain expert who never ever wrote a line of code can still see exactly where the robot made up its mind. So that's what we talk about when we're saying we're reading the robot mind. We're actually seeing where these decisions are made, but you don't need to be a programmer to do it. The visualization and presenting the data in a format that you're already familiar with, or in this case, a subject matter expert, that's really the difference about reading the robot mind. It's not some dashboard or some charts or tables of numbers that tell you how the AI is performing. It's really showing you visibly what's going on inside of that neural network. So we'll also take a look at the autoencoder network. That's where we train a whole nother network to learn the inverse mapping. So this is the most expensive one computationally to go ahead and calculate. But basically, it took the outputs at each layer and attempted to recreate the original input. And you see that even though after we said by this layer, this layer two or the third box here, it already had made its classification and kind of already separated into blobs, but still there was enough information in that data to go ahead and make a pretty decent recreation of those two rings. So that's quite interesting. We can see that even though the neural network has discarded a lot of information and has already made up its mind by that layer two or that third picture, still the autoencoder can learn to see that yes, it has maintained some of the original input information. So although the autoencoder is kind of able to reveal that input recreation information is kept for deeper layers than the other two methods showed, it's still the autoencoder does fail cleanly at the same point the other methods do, and that really proves the network already made up its mind two layers before the final output. So going back to that Reddit question, layers that reconstruct the input well, the model is still keeping that raw input information. Layers that reconstruct the input poorly, the model has thrown away information that's and only kept the info that's needed to make the decision. The poor reconstruction is exactly what gives you utility. You can now debug and explain to non-technical experts, and you can also trust whether that model is behaving sensibly. So this is why I replied on Reddit the way I did. Even a non-programmer can now understand what's going on inside of the artificial intelligence solution, and they can just look at these reconstructions and um, and find out more about how the neural network is really keeping data or discarding data as it makes its way from an input to a final decision about whether it's classification, as in the case of this very simple toy example, multi-layer perceptron, or a more sophisticated neural network that might involve audio or might involve text or generative AI like a large language model. We'll go ahead and take a look at those models in the book. I hope you will think about purchasing the book. I am trying to sell a book here, so I will give you the link in the chat area, as well as the link to all of the GitHub. All the code is available to you for free. Go ahead and take a look at it. And also the vibe coding prompt. So in other words, you don't have to write the code from scratch. You can give your Claude or ChatGPT or your Copilot. You can give it the vibe coding prompt that will walk it through how to create a reading the robot mind system, and any one of those three methods: the pseudo inverse, which is just linearly recreating the input; the brute force, which is we keep a big database of example inputs and we just match which ones are closest to the output at that particular layer; and then finally the more expensive autoencoder, where we train an autoencoder to literally try and recreate the input. I hope this has kind of got your gears turning and it makes you want to use the reading the robot mind system to analyze the internal workings of your AI solution and also help you explain your AI solution to non-programmers. Listen, thank you so much for listening and have a great rest of your day.